Welcome, everybody, to today's Colloquium. It's my great pleasure to introduce our speaker today, who is our own Bethany Wilcox, who you all know. Bethany earned her bachelor's in physics and astronomy in 2010 from CU, and her PhD also at CU with advisor Steve Pollock in 2015. She stayed on for a postdoc with Heather Lewandowski and was hired as an assistant professor in the CU Physics Department in 2018. Since she joined our faculty, Bethany has published extensively in the broad area of physics education research, and more specifically in the areas of how to assess student learning and outcomes, mostly in core upper division physics majors courses. Bethany won an NSF Career Award in 2022. She's supervised a large number of graduate and undergraduate students and maintains a large and active research group. Most recently, she's been awarded a CU Best Should Teach Award, as well as an Asset Excellent in Teaching with Technology Award, and a BFA Excellence in Teaching Award earlier this year. Today, she'll be speaking on the topic of developing current and next generation physics assessments. Please welcome Bethany Wilcox.
Awesome. Well, thank you very much all for being here. I'm excited to have the chance to chat with you all today. So today I'm going to talk to you about one portion of the work that I and my research group have been doing around trying to meet physics education's need for both current and next generation assessments. Before I dive into that, I want to just acknowledge many of my wonderful collaborators and graduate students and undergrads whose intellectual labor, blood, sweat, and tears are very much going to be reflected in what I have to chat with you all about today. So, broadly speaking, PER deals with trying to understand student learning. And doing this necessarily has to be a multi-pronged approach. And indeed, my research group has research areas in a lot of different aspects of what it means to understand and investigate student learning. For example, we have some work that focuses on student learning in the classroom. Things like, how do students form collaboration networks? How do they collaborate with each other on homeworks? How do different pedagogical approaches in the classroom, in this particular case homework corrections, influence the nature of collaboration or the nature of student learning in these environments? We also have ongoing work thinking about student learning in laboratory environments outside of the classroom. I have work collaborating with national leadership on understanding REU experiences and how those can help support and develop undergraduates as professionals who are qualified to enter into graduate programs. We also have work looking at that same goal, but instead in course-based environments instead of in the research environment. We also have a large area of work focusing on problem solving. How do we understand the way students reason when they're solving mathematical problems? What kinds of representations do they use? Free body diagrams, sketches, drawings, and how do they reason about complex physical concepts like entropy? All of this work, I am not going to talk to you about. So instead, I'm going to shift to another area of my work, which is in developing research-based tools to measure student learning. So to kind of frame this, I want to ask the question, why should we be measuring student learning? In the context of an educational environment, hopefully the answer to this question is self-evident, but it is worth being explicit about our goals and our framing. So for me, measuring student learning is about grounding pedagogical curricular decisions and curricular approaches in reliable data about what students are actually learning in our environments. Fundamentally, we're trying to ask the question, how can we improve student learning in these environments with respect to our learning goals? But to answer that question, we first need to understand what students are or are not learning within these environments. PER has a variety of methods to answer this question, some of which I kind of mentioned before, which is research on student difficulties, where you simply go in and try to watch students problem solve and see what's challenging about it for them. But I'm going to focus on the slightly more generalizable approach, which is assessing student learning in a quantitative sense. So when you talk about assessing student learning, we do this all the time as educators in a variety of ways. So on one end of the scale, we have very informal methods for assessing what our students know. Talk to them. This is one of the most reliable ways to figure out what a person knows, simply to interact with them. On a slightly larger scale, more on average in a course, you could do something like ask a clicker question, get a general sense of what your students are learning and understanding. Homeworks can also give insight into this. And then last but not least, we have sort of our summative high-stakes course exams. These are all ways that we figure out what our students are learning. Why isn't this enough? And implicit in that question is my stance that it is not enough. But to talk about why this is not sufficient on its own, we need to talk a little bit about some testing theory before we dig into that. So from a classical test theory perspective, in order for a test to unambiguously reflect student learning, it has to be two things. The first is valid. Validity has to do with, does your test measure what you say that it measures? If I say that my test measures student understanding of the force concept, is that what it measures, or does it measure something more like how do they interpret word problems? Which is a related but perhaps not redundant skill. Tests also need to be reliable. Reliability has to do with, does the test measure whatever it measures consistently? You can think about validity and reliability in analogy to accuracy and precision. So here is a test that is quite precise. We have a very nice grouping, but not particularly accurate. So this would be reliable but not valid. Here we have the opposite. This test is overall valid, it's accurate, but it's not particularly precise. Any individual measurement is not particularly reliable. And then lastly, we have what we're going for. We have a valid and reliable and accurate and precise assessment. This is what we're trying to achieve. The primary way that this has been achieved within the field of physics education research is with the development of research-based conceptual assessments. And I want to define for you what I mean when I say that. So these are exam-style, typically pre-post diagnostic exams. One big difference between them and course exams is these are low stakes. They are not graded for students' answers, but rather just for participation. They typically measure some aspect of student learning not typically covered on traditional course exams, tend to be more conceptual rather than mathematical or calculational. They're designed to measure student learning on average, on the scale of a course. This is feedback to you as an instructor, not necessarily feedback to individual students on their performance. They're strongly grounded in research about what we know students struggle with and how students reason. And they're standardized with the goal of allowing for comparisons across different contexts and different courses. And then last but not least, that point that I just made on the last slide, they're analyzed very carefully for validity and reliability. The process of developing these assessments, as you might guess, is a long time-scale process and a complicated one. So this little flowchart kind of maps out basically the process that we go through to develop one of these conceptual assessments. And naturally, right now, it looks fairly linear. It's not linear at all. It's quite iterative. So as we find problems on any of these points, we have to feed back into the earlier stages and make sure that the final product is that valid, reliable test we're looking to develop. So I'm going to use this little map to kind of guide us through the talk. You'll see this pop up in the corners periodically to kind of let you know where we are in this process as we move along. So I, in particular, have focused almost exclusively on developing upper division assessments. So the vast majority of the assessments I've created target junior level content and above. And I want to kind of map out to you the different assessments that I have worked on. The first two are actually some of my older work. These two assessments actually predate me. They were created in a free response format before I took them over, and my contribution to these was primarily the creation of this format. It's called coupled multiple response, and it was an attempt to straddle the benefits of a free response test that has to be graded by hand and the constraints of a multiple choice test, but that can be automated. So this format kind of splits the difference and allows us to still automate grading. They're still closed form questions, but they're two-tiered to offer insight into student reasoning. So we get a little bit of the best of both worlds with this format. After starting here, I worked on two additional assessments, both targeting content from thermal and statistical physics at the upper division level. The U step It was the very first physics-specific assessment ever to include material on statistical mechanics. So that filled a particular void in the literature, a tool that we didn't have before. That assessment is complete and available for use. Then we started working on the Thermal and Statistical Physics Assessment, or TASPA. Now, you might ask the question reasonably, why would you create two tests to target the same material? Well, the reason that we did that is because the TASPA actually does things the U-STEP does not. TASPA is the first assessment within PER to target scientific practices very broadly. So rather than just talking about do students know the concepts, we're interested in can they do the practices that define physics, things like using mathematical models, analyzing and interpreting data, making claims and justifying them, things like that. And then last but not least, I have also worked on two quantum-focused assessments, the QCCS, the Quantum Conceptual Survey, and this is the first assessment that has ever been developed to target basically any aspect of quantum information science. And then the Quantum Physics Assessment, or QPA, which is a very significant experiment. We'll talk about that towards the end. It is going to be the first large-scale, flexible conceptual assessment that allows an instructor to pick and choose what they want to have on their test. Now, once again, I would love to talk to you about all of this, but we probably only have 39 minutes at this point, so I'm just going to focus on those last two. So we're going to focus quantum today. So let's start with quantum computing. Why? Why do we want to create a quantum computing assessment? Well, quantum information science as a field is exploding, both nationally and internationally. And coursework in this field is rapidly growing. You are getting new courses and new programs around the broad area of quantum information science almost daily. But quantum information science courses, and quantum computing courses in particular, are sufficiently different than your standard quantum mechanics course that none of the existing quantum assessments actually really work. They're just not particularly valid for this area. So we have, between both of these, a unique opportunity to provide a tool to the community that will help identify best practices pedagogically for these courses before the curriculum is set, so we can really make sure that this field starts out on the right foot. So there are some challenges, though, when you start talking about quantum computing education. Quantum computing is new-ish, which means there is little consensus on what exact material should be covered in a standard quantum computing course. It's also rapidly evolving, which means even if there was consensus, the coverage is changing. And it's interdisciplinary, which means that the students that are going to be in these courses are going to have very varied backgrounds. So in order to sort of overcome these challenges, we first need to understand how they play out in the classroom. So we wanted to do this. We're going to start from the source. Let's talk to the faculty who are teaching these courses. So we sent a survey out to 116 instructors of quantum information science courses around the country. This is mostly going to be physics, computer science, and engineering. And we got 32 responses, which for those of you not familiar with survey research, that's a pretty good response rate. It suggests that there's interest, that the folks were actually excited to participate in this kind of work. The content of the survey focused primarily on where are these courses being taught in terms of department and who are they being taught to in terms of survey population, what was the expected preparation the instructors or the students would come in with, and any specific difficulties that the instructors had observed with their students. So let's start with survey results. Who are we teaching? Now, I am going to throw up a fairly complicated little representation here, so I'll talk you through it. What we have here, each row in this is a course. And each little dot is 5% of the student population. This is broken down by major: physics, computer science, engineering, math, and other. So the filled in little circles represent people who are in the major where the course is being given. So these are all physics courses, so all of our physics dots are filled in. But none of our computer science dots are filled in because they are taking a course in a department that is not their home department. Now, what I really want you to take away from this representation is that in physics, let's focus there for a moment, many of these courses are primarily teaching physics majors. But there are some notable exceptions where we have situations where the physics students are actually the minority in the class, and you have a considerable number of computer scientists or engineers. The same thing true down here for computer science, where once again, we certainly have courses where they're teaching significant chunks of folks outside of their home department. Now here is a similar graph. Only difference in this one is that instead of looking at major, we're now looking at level of the course. First year, beyond first year, hybrid, or graduate courses. And once again, broken down by the year of the students enrolled. So with the exception, once again, of our first year seminars and our graduate courses, our beyond first year and our hybrid courses really are being taught to a wide range of students. You have as many third years as fourth years, and sometimes as many as graduate students. So we really are seeing that these courses are quite multi-level as well as interdisciplinary. So this really supports our intuition that these courses are very interdisciplinary and taught to a variety of student backgrounds. In terms of prerequisites, we see a strong and somewhat interesting trend that most people who are creating these intro quantum computing courses have made the choice to not require any physics or any computer science. And in fact, they're only requiring linear algebra. That is the trend. There are notable exceptions to this, but this means for instructors in this course and for us as assessment developers, we cannot assume that these students come in with physics or computer science background. Those instructors have to teach that material. They just have to set those students up. And then last but not least, who is doing the teaching? Well, not surprising, I suspect to most folks, physics and computer science are the majority of the folks teaching these courses, with a handful of engineering and a smattering of cross-listed courses. So we know it's interdisciplinary, we know it's multi-level, we're gonna have to deal with those facts, but how do we know what the test should cover? There's a lot of content that could go into this. This is a very new field, so we need to understand what we need to put on this test. So once again, we're gonna return to our tried and true message of ask the instructors what they wanna teach. So we compiled a list of quantum information science and engineering topics. This list was compiled through a series of interviews with instructors and analysis of syllabi that we were able to access either directly from instructors or that are just available on the internet. We sent this survey out. We cast a much broader net this time. We sent this out to 475 different four-year institutions and received 85 substantially complete responses out of that. The survey was designed to serve a variety of purposes, so we were very careful about how we asked this question. We gave them a list of topics that might appear. In this case, this is in the area specifically of mathematics that they might teach or require in their course. And we asked them to rate whether they both covered and assessed this material, covered it but didn't really assess it. Maybe it's a little peripheral, not core to the course. Whether they reviewed it and assumed it was prior knowledge or didn't cover it because it's beyond the scope of the course. We're going to focus in just on the answers to this covered and assessed because we're interested right now in talking about the creation of the assessment itself. So here is the results from that survey. The percentages are those who said that they both covered and assessed that topic. Now, highlighting out of that everything that has at least an 80% agreement, we get these sections of content. Now, for the purposes of the QCCS, everything that is in yellow is what we have attempted to include on this assessment. The other two, which hit that 80% threshold, are fairly application focused, and we decided that we were not going to include those, in part because we weren't entirely sure how to include those on a conceptual assessment. So those two are not in there, but that definitely suggests an important area for future work, that being able to assess applications of quantum computing and algorithms is an interesting area still left open. So all of once we have this list of topics, a list of topics does not necessarily lend itself to writing a question. You could write a million different questions on a single topic. So there's an intermediate step, which is creating what we call assessment objectives. These are concrete statements of what a student should be able to do after a class. So we've broken these up into a few different sections: mathematical foundations, entanglement, superposition and measurement, quantum gates, and quantum circuits. I'm going to throw a handful of these up here and give you a couple seconds to read through some of them. Josie, NMP. Naive measurement probabilities. Thank you very much.
It's a term that we coined in a paper on student reasoning about basically
Yep.
the fact that sometimes they can figure out if a state is not or is entangled. It's not
Just by thinking about measurements in the standard basis. Yep. I want to narrow in on these two because I'm going to show you a couple example questions. So for this first one, mathematical foundations, one of the questions we came up with, we gave the students a sequence of mathematical manipulations and asked them to define what is the nature of the outcome of that manipulation. And the sharp-eyed among you will notice that some of these manipulations are in fact quite meaningless and they're not valid mathematical statements. So undefined or meaningless is the correct answer in some cases. For the quantum gates, one of the questions we came up with is we give the students a quantum gate diagram, a quantum circuit diagram, and we ask them to determine which of the options we have provided is effectively equivalent. So there's some notational conventions built into here and also some understanding of how and when you can flip the order of operations between single qubit gates. So once we have all of our items, we need to pilot test them. We need to understand whether or not they're doing what we think they're doing and whether we're getting valid information about student learning out of them. The first pilot test of the QCCS was in fall of 2023. The beta version had 24 items, and we got data from 18 courses, just under 300 valid student responses. In this process, we also did interviews with instructors to ensure that they thought our questions were reasonable and things that they cared about. And we did interviews with students to make sure that the students were responding in ways that made sense. Their reasoning was consistent with what we were hoping to see. After that, we made some modifications. We dropped 4 of the questions, modified several others, and repiloted this in the spring of 2024 to 41 courses with just under 700 responses, 600 responses. As part of this, we also did 33 interviews on a subset of the questions on the QCCS. That subset of questions specifically targeted the C0 gate and entanglement. I bring this up, it's a bit of a side project, but it actually is going to help us understand something that I'll talk to you about later, because 2 of the items in this interview set actually end up being important to return to later. We're not done yet. I am going to show you data from that spring pilot. We will pilot again in the fall and probably again in the spring. And we anticipate that the final version will have 19 items. There's one we anticipate we're going to drop. So I want to show you some preliminary results. And I want to get into this question of statistical validity and reliability. How do we show that? How do we convince ourselves that these tests are doing what we want them to do? So here is item statistics for each of the 20 items on the QCCS. I want to average right here. This is average out of 1. These are dichotomously scored items. They either got it or they do not. So you can interpret that number as the fraction of students who got the question correct. Discrimination is a Spearman correlation between the, yes? Yes, this is as a post-test. We did not give a pre-test, and we probably will not. It's a good question as to why. The problem is that prior to their class, they won't even know what a quantum circuit diagram is, let alone be able to tell us anything about it. If we did want to do a pretest, the most obvious option would actually be a linear algebra pretest, just to provide a baseline comparison measure. Discrimination is a correlation between the item score and the score on the rest of the test. Thresholds from classical test theory say that you want averages between 0.3 and 0.9, which basically means not too hard, not too easy, and you want discrimination values above 0.3. 3 items on the test highlight as problematic on these measures, 18, 8, and 15. 18, the only thing wrong with it is right on the boundary of that difficulty. It's got reasonable discrimination, and we actually, right now, are planning to just keep that one. It's really close. We think it's actually okay to have some really hard questions on there. This one just is quite challenging, but could serve nicely for overall discrimination. Questions 15 and 8, however, both have pretty poor discrimination. And poor enough, actually, that we're concerned that these will disrupt our sort of view of the test as a whole. So moving on from here, I'm actually going to remove those 2 items from the analysis. But I'm going to return to those items here in a moment, and we can talk about what we think is going wrong with those items. So in terms of overall performance, again, dropping those 2, question 8 and 15, averages are in the 50 to 60% range. So it is a challenging test. That is actually exactly what you want for a conceptual assessment, because it gives you maximal discrimination. In terms of breaking this across majors, physics majors are scoring the highest, computer science and engineering sort of sitting at the average. We're also seeing that our graduate students outperform our undergrads. Yes. 18. Yes, out of 18. So here is a distribution of the scores on the assessment. This is also every individual of the 41 different institutions that gave the QCCS. This is their average and standard deviation. So you are seeing significant variation in how students are performing. So we do think the test has some ability to distinguish potentially between at least different types of classes, maybe eventually different types of instruction. Obviously, we don't know that yet. Just to dot the I's on the classical test theory, 2 other things you want to test. Whole test discrimination. You don't just want items to discriminate, you want the whole test to give you good discrimination. Ferguson's delta is the statistic that tells you that. It needs to be above 0.9, and we have 0.98, so we easily meet that threshold. Whole test consistency, which you can think of maybe as another way to measure unidimensionality. Measured by Cronbach's alpha. For group assessment, not individuals, but for group assessment, we want that number to be above 0.8. And once again, we are meeting that threshold. So overall, it's looking good. QCCS is looking pretty solid on classical test theory measures. But is this enough? And as you might guess, because I'm asking the question, my answer is no, it's not. So I want to talk about why. Why is this not sufficient in this particular case? And I want to bring this back to the unique challenges that quantum computation presents. So we've already convinced ourselves that quantum computing courses are interdisciplinary and multi-level. We would really like to be able to make comparisons between student performance across these disciplines and across these levels. This is unfortunately not something that classical test statistics do well. They're highly sensitive to population variation, and so we just don't feel like this is sufficient for us to justify making those kinds of comparisons. So we need something else. We need to go a little bit more sophisticated. Luckily, that sophistication exists, and we have options beyond this. Now, we're going to talk a little bit about the specific case of item response theory, but testing theory in general, whether it's classical test theory or item response theory, looks to answer the question, how do we quantify something we cannot directly observe? I cannot, unfortunately, open up my students' brains, look at that corner and say, oh yeah, no, you're good at this. That's not possible. Even if it was, I suspect it wouldn't be ethical. So we're trying to get a proxy measure. So in particular, we're trying to create a scale. In test theory, the scale is typically denoted theta, and theta is the latent trait that we're trying to measure. Educational literature often calls theta student ability. That's a little bit of a problematic name because it's at best a proxy for student ability, but it is what they use in the literature, so that is what we're going to use here as well. In addition to caring about student ability, the other thing that item response theory cares about is the difficulty of the items. So B is the difficulty of the ith item on the test. So we're going to dive into one of the simpler item response theory models, which is rash modeling or rash analysis. And rash analysis makes several assumptions. It assumes that theta is well-defined and unidimensional. It assumes that the probability that a particular student will answer a particular item correctly depends only on the ability of that student and the difficulty of that item, nothing else. It also assumes that the probability that that student will answer the item correctly goes to 1 at large theta and goes to 0 at small theta. High ability students should answer all questions correct. Low ability students should answer all questions incorrect. Under these assumptions, items will obey the Rasch model. And specifically, the Rasch model is able to output population and test form independent statistics on theta and b. Yes? So the range of theta is nominally out to infinity, but it's going to actually, the item response curve will go to, depending on the population, it'll happen at like plus or minus 2. It's typical. It's a logit. Theta can be negative, yes, because it's going to be standardized. We're going to actually just put the middle of theta right at 0. OK, so here we have our Rasch model. If an item obeys the assumptions and student responses obey the Rasch model, they will obey this mathematical form, which is going to give you what's called an item characteristic curve. And these item characteristic curves look like this. So just breaking it down theta in logits on the axis here. Again, it's standardized, so we just put the 0 point right in the middle. So we can go positive or negative. And then we have the probability that a student will answer the item correctly as a function of theta. So there's 3 different curves on this. I will draw attention to the fact they all have the same shape. That's actually a requirement of Rasch analysis. That model does not allow them to have another shape. And these difficulties are defined by the inflection point of these curves. So for example, that center one, the inflection point, the point where a student with an ability of 0 has a 50% chance of answering this item correctly is at 0, and so that's the difficulty of that item. Oh my. Oh, we're good. Okay. All right. Same with the other 2. So this item would be given a difficulty of -1 because that 50% inflection point happens down here at -1 and 1 here. So this is how we're defining the difficulty of the items. Yes? You're concerned about this?
Yeah, like is there something in the model?
Yeah, so this is actually coming from another assumption of Rasch modeling that I didn't call out, which is it assumes a standard discrimination. So what is encoded in that slope is the discrimination of the item. There are other item response models that allow discrimination to vary, in which case you will have varying slopes there. But one of the assumptions I did not call out is Rasch modeling does not allow that. Some challenges to the Rasch model, which I think some of you are kind of narrowing in on, understandably. Unidimensionality is a pretty tall ask for a conceptual assessment. To argue that quantum computing is unidimensional is interesting. We'll talk about that in a minute. Items must be independent except through theta. I think all of us have experienced situations where the ordering of items can impact how students respond. That would not fall within the Rasch model. You need dichotomous scoring unless you have fairly big data sets. There are polytomous item response models, but they require a lot of data to lock in the parameters. There's no allowance for random guessing, and there's no allowance, as we just mentioned, for ranges and discrimination. This is pretty strict. And the answer to this is that you don't assume tests do this, you make tests do this. So you often have to discard items that don't meet the model. And they may be promising items, and you may not know why they're not meeting the model. But if you want the benefits that Rasch modeling gives, you simply cannot have items on your test that don't meet the model, and you just have to test that and eliminate any items that do not. So how did it go? Well, perhaps surprisingly well. And I say perhaps because we actually designed the QCSCS very intentionally. We knew from the beginning we were planning to do this. We made very intentional choices about what questions we chose to ask, what formats we chose to ask them in a way that we were always working towards this as an end goal. And it seems we did fairly well. So 18 of our 20 items exhibited fairly good fit to the Rasch model. And surprise, surprise, the 2 misfitting items were items 8 and 15, which were the items we already flagged as being problematic in classical test statistics. Overall fit indices for the entire test are also acceptable. I will note they're not good. We would like them to be better, but they are in the realm of we're getting close. And we still have more pilot testing and more revision to undergo here. I want to just throw this up here because we did talk about those item characteristic curves. These are the item characteristic curves for the 18 items that we're considering here. Again, item 15 and item 8 are not on this. And what you'll see is the red is the model, that's the output of the RASH model, and the blue is data. And we're seeing pretty significant overlap, pretty significant consistency. There are still a handful of places where we're getting deviations that we're going to want to look into and think about whether or not we can make modifications to the question to better align some of those wings. But overall, we're getting pretty consistent information here. Yes? How is theta estimated? So this is, for right now, I'm just going to say this is a black box. It's estimated, this is something you do through statistical packages like SPSS or R. So it's an iterative process to estimate. Yeah. So I do want to narrow in on those two poor performing items because I think you can actually learn a little bit about some interesting things because these items performed poorly. So in this case, this is question 15. This question involved feeding in a superposition state into a fairly simple quantum circuit involving a C0 gate and then a measurement on the target qubit. And then we ask whether or not that measurement can impact the state of the control qubit. This is the item characteristic curve for this particular item. It does not look like the other ones, and that is what we're seeing when we look at those fit statistics. So what we think is happening here, and this is in part informed by the interviews that we did with this question, we think that the limited options lead to guessing. So there's a significant guessing effect here, which again is not accommodated by the RASH model. And there is a very tempting sort of gut intuitive response that happens to be incorrect, but incorrect for subtle reasons in this particular case. And so this question, it is a challenging question, and it seems to basically, we've got people on the low end who have just as good a chance of answering it as people over here in the middle, and only a tiny bump at the end. We think we can salvage this question. We are trying to revise this question to address these issues. The other question that was poor performing is question 8. I'm not going to read all the stuff that's on here, but this breaks down to you are considering the possibility of the difference between buying a 500 qubit processor or 2 simultaneous but independent 250 qubit processors. And is that the same thing? Should you do that? Now, the problem with this one is sort of similar. Looking at that item curve once again, we're really just not seeing very good discrimination here. There seems to be a lot of maybe guessing going on. We also think from the interviews, something happening here is that the reasoning elements that we have provided for them to select tell us more about why they chose the answer they did. The correct ones are also just true statements. And so we think what's happening is that students are basically able to kind of look at the answers, select the true statements, and then kind of reason their way backward, but without really understanding the deeper connections there. This question, while we think this is a fun question, this one's likely actually to get eliminated from the test. We don't have a lot of good ideas for how to make this question better. So I want to return to this question of unidimensionality. And the question, is quantum computing unidimensional? Probably not. Yes. Unidimensional meaning there is a single underlying latent trait that governs how good you are at it. There's not multiple things. Like you could imagine one concern might be like linear algebra skill versus physics conceptual understanding. Maybe those are 2 different dimensions. Maybe you have 2 different ability levels there. Maybe that's a concern for unidimensionality. But fundamentally, the question is there a single underlying trait that governs how well you do on this? So I kind of doubt that quantum computing is unidimensional. But the question we actually need to answer is the QCCS unidimensional? And I'm going to argue we also need to ask the question, is it unidimensional enough? Is it close enough to unidimensional that we can still meaningfully interpret students' responses in a way that helps us understand what's happening in our class? So one way to do this is actually just to do a factor analysis and look at how this is all playing out. Yes, Oliver?
Is anything
A very fair question. Is any physics subject unidimensional? What? Is any subject unidimensional? Which is why I introduced this comment about unidimensional enough. Feet are also not unidimensional, and yet we typically use one number to determine which shoe you wear. And this certainly leads to problems and uncomfortable feet at times, but it does the trick most of the time. So is it unidimensional enough, is the question I want to ask. And when you do a factor analysis on students' responses to the QCCS, I think the answer is sort of. There certainly is one dominant factor. So if there is a dimension the QCCS is measuring, it's that one. Interesting to ask what that one is, but it also has these two smaller factors here, which by several ways of thinking about what is significant on a factor analysis, those are not insignificant factors. Yes. So you can think of a factor analysis as, let me try to use a vector analysis analogy. If you have a number of different vectors, you can think of each vector as a question on the test. A factor analysis is trying to sort of rotate the coordinate system in such a way and create another vector that mostly captures this bunch of vectors, and then another vector that mostly captures this bunch. So it's trying to reduce complexity of a test from 30 items down to some number of factors. Yes, exactly. It's eigenvectors of the matrix. So the takeaway for us in terms of QCCS is that the limitations that we have on the Rasch model may well fundamentally be about unidimensionality. Now, we can still tweak this. We are, again, still in the pilot phase. We can still make changes and try to improve model fit. But the majority of the QCCS items are performing within accepted classical test ranges, and the whole test is largely performing well on Rasch analysis. What this means for us is, especially with a little bit more work, we think that cross-level and disciplinary comparisons using the QCCS are going to be valid. We're going to be able to do that in a productive way. And I will say, I did not talk about this, but that conclusion is also supported by complementary differential functioning. So we looked at differential performance between these different groups to try to understand how that was playing out as well. Another thing I wanted to just mention, QCCS questions eventually, especially once finalized, will prove a nice testbed to understanding students' difficulties with some of this quantum computing content, which you really have no information about this, at least in the literature. So for example, we have ongoing work using QCCS questions to try to understand difficulties around using the C-NOT gate and its relationship to entanglement. Okay, with the remaining time, I want to sort of step back, because the QCCS, while novel in a number of ways, both in terms of content coverage and its connection to sort of being validated with Rasch analysis from the beginning, is unique amongst physics education research assessments. It is a current generation assessment. It's not really incredibly novel in any other particular way. It's a conceptual assessment. We've been making these for many years. And these current conceptual assessments, they meet some, but not all of the needs of physics education. So some of the things that are challenging about current generation assessments, they're narrowly conceptual focused. Turns out concepts aren't the only thing that matter in physics. We might want to test some other stuff. They typically have a static format, which means that if you don't teach exactly the same things that the test tests, then you may not really care about how well your students do on it. And they can be hard to administer. Faculty have to find the test, administer the test, sacrifice a class period, analyze the results. It's a whole thing, and we're busy. So I actually have work that is trying to address all of these limitations. I already mentioned that the TASPA is working to incorporate scientific practices into our physics assessments. I'm also exploring modular and test bank models to address the issues of static format. And then lastly, I've been working with a number of others, Heather Lewandowski being among them, to transition to online central platforms that really reduce the amount of work that an instructor has to do to be able to utilize these. With the time we have left, I actually want to dive into just this one, exploring modular or test bank models. So that second assessment that I told you we were going to talk about, QPA, which stands for Quantum Physics Assessment, is going to utilize a flexible test bank model. So in terms of how this will work, the plan is we will have a bank of possible test items. The instructors will choose which of these items they want to use. In fact, they won't actually choose which items they want to use. They're going to pick some of those assessment objectives. So they're going to choose what they want to test on their exam. Then our system will create the assessment for them based on their choices. It will collect all the data, analyze all the data, and send a report back to the instructor to help them interpret their students' performance. Now, there's so many advantages to this. One of the main things, it can accommodate variable format, variable content coverage. It's also perfectly capable of accommodating differences in standardized notation. Quantum computing is a place where this is a problem. It can also potentially accommodate differences in instructional approach. It reduces the administrative burden for the instructors. This necessarily has to be an automated and online system, which means we can leverage all the benefits that come along with that. And it centralizes data collection in a way that lets us facilitate large-scale comparison. But there's definitely some disadvantages here. And most notably, it's a really heavy lift on the validation side. All of those constraints I talked about with rash analysis, they're all still there. And so we still have to deal with that. We have to validate this with IRT because we need test form independent statistics. We need large data sets in order to be able to do that. And as I mentioned, it has to be administered online. It is also a very new model for instructors. And I don't want to downplay the importance of that. This is a completely different way of thinking about how you assess your students than what an instructor is used to. And we need to be very careful to design our system ahead of time to accommodate this difference in expectation and this ability to dive into this new interface. So our model for the interface that the QPA will use, an instructor will come and say, I would like to give the QPA to my students. They will then have 3 different options for how they can decide to do that. They can either use one of the several existing quantum mechanics assessments. Maybe they've used them in the past. Sure, we'll give you one of those. They can create it based on a textbook by just telling us I teach these chapters of McIntyre, for example. And then we'll just kind of create one that matches those chapters of McIntyre. Or they can do what I suggested before, which is go straight to our assessment objectives and fully customize the exam. In these 2 options, we need to also take into consideration how long. We don't want to have them giving their students 100 different questions, and how hard. We also don't want them to select all the really hard options or all the really easy ones. So we'll provide guidance on that, and then they'll have the opportunity to preview and finalize the assessment for their students. Now, we have actually tested this interface in interviews with faculty, 34 faculty at 33 institutions, and the majority of them responded quite positively to this. They like the flexibility, they like the ability to customize all of these different things. They do naturally have some concerns and some suggestions, and we'll be able to integrate all of that into the system moving forward. So where are we on this? Well, we are currently in the process of developing our test bank. Now, Quantum 1 is easy enough. There are already, I think, something on the order of 8 assessments, static assessments, that have Quantum 1 material on them. And that gives us a test bank of 149 items. They've already been tested with students and with faculty, so we know faculty like them, students can respond to them. And there's a significant amount of redundancy in that set of questions, so that when we do lose items to meeting the model, we will still be able to fill out our full learning goals. Quantum 2 is harder. There is no existing static Quantum 2 assessment to pull from, which means we are back to the beginning. We have to start this process all over again, right where we started with the QCCS. We have to figure out what to cover, and we have to develop assessment items to do that. Now, we're going to do this in the exact same way we did this with the QCCS. I will not bore you with the details. We sent out a big survey. We got 76 responses back. This is much newer. This is sort of right off the presses, so I don't have quite so pretty of a representation for you all. But here is the list of different topics that we provided and the sort of ratings that different faculty did. This is 76 responses. These are fractions of that response. Green right now is highlighting everything that went above the 70% threshold, although we will certainly do deeper analysis of this to understand what is important for us, for example, just quantum 2, which is what we care the most about here. So we have already started to work on this to create assessment objectives. So for example, here's 2 assessment objectives we've developed for perturbation theory. Given a relationship between unperturbed energies and the strength of a perturbation, a student should be able to determine if perturbation theory is applicable, or determine if a system is degenerate from the unperturbed Hamiltonian in a matrix form. So these are examples of the types of assessment objectives we will develop. So in terms of future work, we have a lot yet to do with CUPA. We're early in this process. We're 2 years into a 5-year grant on CUPA. We need to develop a back-end algorithm for how do we go from list of assessment objectives to comprehensive questions, exam. Luckily, we have a lot of literature to pull from that in the realm of computer adaptive testing. We actually have less of a challenge than computer adaptive testing does. We need to develop additional items. We have started doing this, but we need a lot more, and we'll be doing student and faculty interviews with all of those new items. And then, of course, we will have the challenge of large-scale pilot implementation and going through that IRT analysis and then iterating. So we have a long ways to go, but a solid base. All right, we're at 4:50, so I'm going to talk for like 1 more minute, and then we'll have time for questions. I want to return to the sort of comment that I had at the beginning that understanding student learning is a multi-pronged approach. There's no one thing that you can do that will really answer all the questions you might want to ask. So I've talked extensively now about developing research-based tools to measure, to quantify student learning, but this has to necessarily be complemented by a lot of other and often more qualitative approaches. So for example, investigating student problem solving, you can't do that necessarily with a test. You just have to sit down and watch them work. Exploring the student experience, understanding what happens in the classroom and how do the students interact with that and what influences their ability to engage. Identifying effective educational environments. You can point to them using quantitative statistics, but to understand why they work and how you might transfer educational environments, you have to go in there and watch them happen. And then lastly, addressing inequities in current educational systems necessarily requires really talking to people, especially people who are not majorities in those educational environments. So while this has all been very quantitative, I also want to just emphasize that understanding student learning needs to be an expansive thing that involves a lot of methodologies. And with that, we have time for questions, I think.
Professor Finkelstein, I saw your hand first, and I'm going to give you a mic. Well, you don't need a microphone. I know you.
Not if y'all can hear me. Bethany, thank you. What? Thank you so much. Fabulous work. I hope you don't feel that you are responsible for figuring out all of the student experience in educational environments as you had on the last slide, but you're making huge contributions. It's very clear. Based on the computer adaptive testing model that you were just chatting about, that strikes me as sort of AI 1.0 style work. Could you comment a little bit about where generative AI and sort of that may go with this? For example, you find that the major driver to multiple choice response or coupled multiple choice was led to because of bandwidth issues. Might that be going away in the future? Is that a big scale future or problem?
Yeah, it is hard to make predictions. I mean, my short answer is no, I can't comment on this. My longer answer is yeah, absolutely. This is gonna, AI is advancing in a significant way. Natural language processing models and things like that are certainly going to make waves in like our ability to do things like take free response questions and run them through that so that they can be auto-scored. I mean, you and I have discussed the limitations of this, especially in particular areas, graphing, anything pictorial. AI is not anywhere close to being ready for that. So I think in the longer scale, yes, that's a direction that is valuable. In the shorter time until we get to the point where that works, stopgap.
Okay, well, thanks, Bethany. That was a really enjoyable colloquium. I just wanted to follow up on my question before about this unidimensionality. Is that what it was?
Yeah.
So I said, is anything unidimensional? And you sort of said, well, it needs to be unidimensional enough. So I was just wondering, we were talking about quantum computation there, but are there examples of different disciplines in physics where you feel like this one is unidimensional, but this other one maybe is not? I was thinking an example like that might give me a sense for that whole process.
Yeah, it's a really good question. I think this is a huge challenge to IRT. I'm not going to use an example from physics. I'm actually going to use an example from national scale testing. The same models that are underlying what I'm talking about here also underlie the SATs, the ACTs, the GREs. So they are assuming in their analysis that quantitative reasoning is a single dimension and asking many questions around that. And I think, again, we might legitimately ask, can you honestly say that there's a single underlying ability that coherently maps out all of quantitative reasoning or all of your reading ability or anything like that? And the answer in practice is no, but it does so well enough that you can use it for the right things. So as with any model, it's a toy model. It doesn't describe everything. What you need to understand is the limitations and where you can bend the rules and where you cannot.
So I came in a little late, so I'm sorry if you covered it in the first, before I showed up. But I'm wondering, so you talked about assessing quantum computing course, but then it seems very obvious, like there's linear algebra and other prerequisites go into it. Like, so it would be nice, but maybe very challenging to kind of first assess how well the students have done in courses that are prerequisite that feed into, that's because their difficulties may be, predating the course or predating the sort of the.
Yeah, for sure. No, I absolutely agree. And we did talk a little bit about the prerequisites, and really it is only linear algebra is kind of the only thing that most people are requiring as a prerequisite for your intro quantum computing course. So yeah, I think the difficulties with linear algebra are huge in this context, especially because some of the linear algebra that you need for quantum computing isn't covered in many linear algebra courses. Tensor products, for example, are not actually covered in most of your undergraduate linear algebra courses. So
what about quantum mechanics?
Quantum mechanics is not required for most quantum computing courses. It's actually quite rare, not even modern, and no computer science either. Most people, because I think from interviews we know this is because of the interdisciplinary push, because faculty teaching these courses really want to be able to engage with the interdisciplinary nature of quantum computing, they cannot require something like quantum mechanics or modern without eliminating computer scientists. And they can't require something like discrete math or computer science 101 without eliminating the physicists. So they're just kind of put into this position where they're going to need to teach the foundations that these students need in the context of the course. Yeah.
So somebody's hand up.
Hi, thank you. My question is if you can elaborate a little bit more on your rationale for selecting the sample size in which you test the instrument.
Oh yeah, that rationale is actually really easy to articulate. It's who we can get to take the test.
It's two questions. Okay, yeah, and so what would be the external validity of that if the the student classroom is really diverse? Yes,
while rationalysis does give you a way to deal with variation in population as long as you have a broad enough test sample, if you go to a sample that isn't included in your test population, it's no more valid than classical test theory would be. Certainly I can't give this to 12-year-olds. It's not that population independent. So you do have to get these relatively large data sets, not only for the the need to have enough statistics, but also to make sure that you have a diverse enough population. And we've pushed really, really hard on that. I will say that 550 doesn't sound like a lot to physicists who are used to getting larger data sets. From an educational perspective, that is a larger data set than what many assessment instruments have ever been tested on, let alone that was only our second pilot. And we plan on 2 more before going live. So we're pushing really, really hard on trying to make sure that we have a large and diverse student population so we can confidently say our test is valid for the broad undergraduate physics and engineering population.
About a third of a way into your talk, you showed a histogram, a distribution of average exam scores. Could we look at that graph again? And you...
Oop, too far.
That was it. That
This
was
one.
it. Yes. Yes. And underneath you have, great. Yeah. And underneath the histogram, you've got, are those different courses in
Yes.
different institutions?
Yes.
Yeah. So clearly some courses do well and some courses do not so well.
Yeah, I'll call out this course up here. That's like a 16 out of 18.
Well, have you mined those courses to see what are the characteristics of great courses and what are the characteristics of not so great courses?
We have not, and we absolutely will.
Well, actually, I've got a follow-on to that, and then which is that if they score well, does that mean it's a great course, or does it mean that your set of questions happen to line up well with what they were teaching? Because there's a lot of variation, as we know, in these early generation courses.
Yeah, it's a great question. I think we can't know that until we do dig into it, and I think you've just kind of put the nail on the head of why flexible assessment is so critical moving forward.
Okay, we're getting close to 5. I'm going to take one more question, but anybody else who has questions, please accost Bethany afterwards. But let's give the last question to Eric.
I'm really interested in this idea of sort of eigenvectors that describe most of the variability in students. So I'm thinking like StatMech or those things. Have you gone, like, suppose you've got, I don't know, 20 questions or whatever it is on these standard things. You find, yeah, whether it's 1 or 2 or 3, vectors that account for most of the variability. Can you take these eigenvectors back to the instructors, to the people who just love this kind of stuff, and can they look at them and can you talk it through them and can they think, oh, maybe does this help me understand what are like the 3 main ideas I'm trying to get across in this class?
Yeah, this is a really good question, and I'm going to give you a somewhat, Debbie Downer response, which is that unfortunately, some of the time there is that coherence in the factor analysis, and you can look at the items that load onto particular factors, and you can say, oh, that makes complete sense. Most of the time there's not. Most of the time, the factors to an expert who has an already sort of well-defined idea of what they think the structure of something like quantum computing is, some